So, this morning, something a bit different, but kind of the same. So, last week we looked at how do you get out of the digital and into the physical to make something that you can make yourself, right? Maybe in the workshop, or get 3D printed, or even just print something out onto paper. It's taking you out of the digital into the real. This week, it's a bigger question. It's the same question, but it's just bigger. The same question is, how do you do something in a computer that makes a difference to a real building? Make sense? Because you can't today go to the workshop and build a building. I mean, you could, but if you did it on your own, it would take you a long time, and it wouldn't be very big, and it wouldn't be particularly good, I think. I worked with an architect for a few years. We had our own practice together, and he's a lovely, lovely guy. And he decided that what he wanted to do was build his own house. And when he said build his own house, most architects think what you mean when you say building your own house is design your own house and then give those plans to a builder who builds the house for you, right? That's what people think when they say, I'm going to build my own house. Maybe you have this as a dream, like one day you'll build your own house. He meant it differently. What he meant was every brick, every bit of timber, every bit of steel, he was going to put in place in his house. So he learned how to lay bricks. He learned how to dig trench foundations. He learned how to weld steel. He learned how to make doors fit. His house is beautiful. The amazing thing about his house is there's always something going wrong with it. And there's always something falling apart with it. Because the nature of building is that it's a collaboration. It's actually quite weird to have one person build the whole thing. It also took him 8 years. He thought it'd be done in a couple of years. And he had a family, and they were living in like half the house, and it wasn't built. And oh man, when you say build your own house, work with some other people to build your house, right? And the reality is that these days, if you're going to build a building, you're going to do it in team. You're going to do it with other people. Everyone else is going to be involved, from planners to structural engineers to mechanical and electrical and plumbing engineers, and especially if that building is big. So as architects, how do we fit into this ecosystem? Because no one really cares if you have like a really nice Rhino model. At the end of the day, in the real world, if you have a really nice Rhino model, everyone's like, yeah, great, this looks nice. But how are we going to build this thing? How are we going to get it out of the computer where it currently lives? And how are we going to give it to a contractor, a group of contractors, a group of builders who are actually going to dig the ground, lay the bricks, erect the steel structure, put the bits of timber together, whatever it is. And the answer in today's digital ecosystem is something called building information modeling, which sounds like, I hope you agree with me, the most boring thing that you could imagine us talking for 2 hours about this morning, right? Yeah, I take your silence as agreement. BIM it's BIM, BIM. It is in practice something that you associate with the kind of character traits that go along with, like, I don't know, accountancy or like legal professions. And you know that you meet the kind of people and they're like, actually, you can't do that. You're like, that's what BIM is like in the real world, except for the fact that it can be really, really powerful. And it has to be very powerful, because what we're trying to do as architects is change the built environment in which we live. And we have to do it through the medium of the tools that are available to us. And those tools are very, very powerful, but they're also a bit overwhelming at times. So what I'm going to do today is I'm going to talk a bit about BIM, give you sort of a little introduction, and then I'm going to contextualize it into the fact that this is my job. I'm the guy in my firm who's like, actually, the rules say that it has to be 5 meters away from the fence. I don't do that often, But in the digital world, I do. So in the digital world, I keep everyone working together, and I keep our projects from basically blowing up and falling apart. And so BIM is part of my job. It's not the whole of my job, but it's part of my job, and it takes up quite a lot of my time. Plus, this is the cool thing, I work for an architecture firm that does fairly large projects. Have you visited the new building over the other side of the road? That was my firm. And the nice thing about the fact that it's my firm is I can now take you through the model, the building information model that was used to build that building. So we're going to tour that through, and then you can go and visit it, and you can see, oh, this thing that an architect did in a computer made its way through to this thing that you can walk and live in and study in. Or don't live in it. Unless rent's that high that you can sleep under a desk or something. Right. So let's go back a few steps. Generally speaking, the traditional way of thinking about what architects do and produce is that you produce drawings of buildings. You don't produce buildings unless you're my friend who's a little bit crazy in the head and decides to want to build a building himself and be architect and builder at the same time. But really, what you produce is drawings. You produce these kind of flat 2D things that you print out on A1 paper, and then you give those things, traditionally, to a builder who then looks at them and then screws them up in a pile and puts them on the corner of the building site and then just does it his way anyway. Or if they're a good builder, they read the plans and they say, oh, okay, right, so what you want is, let's have a look at this. What you're asking for is like a wall here. Well, how long is that wall? Okay, I'll get my ruler out and I'll measure off the drawing and I'll scale it up by 50 because this is a 1:50 drawing. And then I'll go to site and I'll walk out and I'll put a stick in the ground there. And then I'll measure out 50 meters and I'll put another stick in the ground here. And then I'll tell my bricklayer subcontractor to build a layer of bricks that goes between that stick and this stick. Like that's basically a description of how you build a building. And do you see how far apart what you do as an architect in a studio and what actually happens on site can be in that situation? Because effectively you are, and I quite like this analogy, you're like a composer who writes a score and then you send that score to an orchestra and they perform the music. Yeah, and this is your score. This is the only thing that you can produce. Now, if you're very lucky, you get to be a composer who also conducts the orchestra. And you get to visit the site and you get to say, no, that's in the wrong place, move it there. Or, why have you done it that way? That's not how I drew it. Or, oh, that's actually a bit better than what I was drawing. Thanks. Could you let me know how you did that? Actually, it's more the third one than the first two. But anyway. However, let's just take one tiny thing on this plan. What have I circled on there? A door. So you know the language of drawings, right? You know that looks like a door. Does anyone recognize this building, by the way? No reason why you should.
Is it Alva Alto?
It's Alva Alto. Do you know the name?
No, I don't.
It's Villa Maija in Finland, in the middle of nowhere. It's like in a forest. It's a very, very cool building. The reason why skate parks are the way they are, you know, this like swimming pool with a bowl, is this pool in the top right of this building. This is the first like pool with a curvy shape. And everyone was like, wow, this is cool. And then they started building them in like the west coast of America. And then when they empty out, people skate in them. And now skate parks are basically built on Alvar Aalto's idea of a pool. That's a side. But let's look at this door. Because Alvar Aalto has produced one drawing of a building. He doesn't just give this drawing of a building to a builder and say, go and build this. He also designs the door handles. So he's working at multiple scales, right? This is kind of what architects do. You don't just design the building at 1 to 100 and then say, oh, hey, Kate, I know these rooms go here, I'm done. You then go into the detail of each room and what's the floor finish going to be like? What materials are you going to use? What specification are you going to give for the windows, the walls, the doors, the roof covering? How is it going to react to sunlight, to heat transfer? All of these things. This is where technology and design and the digital, they all come together. So this is, 1939, before computers are anywhere near being used for architectural design. But he's drawing every detail all the way down to the detail of the door handle. And he gives that to a manufacturer who then bends it out of brass. And it is a lovely, lovely building. One of the things I love about it is the fact that he wants the tactile experience of opening a door to be a certain way. So he has a brass door handle that's wrapped with leather. So it's warm and cold at the same time. It's lovely, lovely sort of little touches. So rather than touching the door handle and being like, oh, it's a bit metal and cold, he's got this kind of soft thing to it. Now, what I want you to do is have a think about something nothing to do with buildings at all. I want you to imagine you bought a t-shirt in a shop, or you're looking in a shop for a t-shirt, and there's a label on that t-shirt. What I want you to do is take 30 seconds with the person sitting next to you, name as many bits of information as you can imagine being included on that label. Yeah? Just thinking about t-shirts now, we're not thinking about buildings, but it will be relevant to buildings. Go, go, go. 30 seconds. Okay, I was going to write these down, but there's no board rubber, so we'll just have to go through. So don't be shy, shout out. What kind of things are you going to find on a label for a t-shirt? Let's start somewhere at the back over here. Price? Yeah. Where it's manufactured, where it's come from, yeah? Made in China, made in Taiwan.
Size.
Sorry?
The t-shirt size.
The size? Yeah, how big it is, yeah. The material that's used, yeah.
The brand name.
Brand name, yeah. Who manufactured it, who's put it together. There might be multiple people who put it together, but yeah, brand name.
Instructions of use.
Instructions, how are you going to use it? How are you going to
Wash
it, care for it? How are you going to make it last longer? Yeah.
Price.
Yeah, price. We've had price. Anything else?
Ethical impact.
Oh, ethical impact. Yeah. As in, like, were any slaves used in the manufacture of this t-shirt? Because they put stamps on that. Yeah. This was made with slaves. Yeah. There you go. The slave stamp. Yeah.
They might throw in it's zero emission, sustainable.
Yeah, they might put in some kind of embodied carbon thing, or you could potentially work it out. If you knew the material and you knew the country of manufacture and you know the brand name, you could then potentially, you've got enough information to go and find whatever sustainability metrics they might have. Anything else? I'm trying to think. There might be more things. What I want to do is then just take all of these things that you've listed. There are probably more, but this is a really good list. And go back to thinking about this one door handle in one part of one building and think the same amount of information is available for that door handle, right? Where did it come from? How much does it cost? How are we going to look after it? How are we going to make sure it lasts longer? Can I use a particular chemical on it, or will it break? Which manufacturer do I need to go back to? Does it have a warranty that's going to run out after 3 years? If it does have a warranty and it breaks within that 3 years, what date does it run out? Imagine how much information you can cram into just thinking about one door handle, right? And then imagine that the building that we're standing in probably is made up of, realistically, I don't know, let's take a guess. 100,000 parts, like the number of actual little components that go together to make a building, maybe 100,000 of them. I'm just guessing, right? But you've got multiple layers to every wall, and you've got sheets of materials, you've got individual screws. Maybe there's 150, maybe it's 200,000. And every single one of them has the ability to have information associated with it, which might be critical. If we think, I'm going to mention a little bit in a while about Grenfell. And Grenfell is something that hopefully we're all very much aware of, that should be seared in the minds of architects now, because what went on with Grenfell, the thing that went wrong with Grenfell, the fire disaster that happened in London, was that the architects specified a certain number of materials to make up the cladding that went on the outside of the building. And rather than saying, let's make sure this isn't flammable, they basically said, it'll probably be okay. And it turned out that that particular combination of materials made for an incredibly flammable outside of a building, and the fire that started inside actually went up the outside of the cladding of the building and killed a lot of people, and has to now completely change the way we see our architectural responsibility as someone who designs buildings that can kill lots and lots of people that live in them or work in them or whatever. Now, if instead of someone sort of sitting there thinking it'll probably be okay, or I think this person said that about this thing, I'll give that a tick on paper. If instead we had all the information at our fingertips and we shared that information with the right people who would be able to say, hang on, I can see a problem here. And maybe there's a fire engineer who then has access to that information, who can then make a judgment on the fact that maybe today, if you wrapped this particular door handle in leather, they would say, well, I've got some ethical concerns. I've got some embodied carbon concerns. And then you have this conversation before the thing even gets built. That's what building information modeling is trying to do. So what we're trying to do in BIM is facilitate that collaboration. So a design team, let's think about the new Brooks building. How many architects working on that building, do you think? 14. Yeah, all at once? Good guess, yeah? Any less, any more? That feels about, it's a big building, right? You're not going to do it on your own. Actually, there were probably, in total, it probably passed across the desk of around 10 or 12 architects. Not a bad guess. However, at one time, there might have been 5 people working on it, or there might have been 1 or 2. And it depends on what stage you're at. It depends what the timescales are. But yeah, you might have 5 people all at the very, very same time trying to design a building together. If you try and do that with Rhino, what happens? Well, yeah, what tends to happen is you go, hey, could you build that bit and I'll build this bit, and then we'll kind of bring the files together. We'll like import one into the other, or you'll kind of like, you can't work on the same file at the same time, because if you try and open it while someone else has the file open, it'll be like, well, you can't do this. But BIM is a mechanism by which everyone can work on a building at the same time, and all of their changes are tracked. We need information. That's why it's called building information modeling. We're not just modeling a building, we're modeling the information about a building. What's in it, its life cycle, its performance. So is it going to be sustainable to run? Its cost. If you can, in a 3D model, have every single element associated with how much you know it's going to cost to buy, then you can give that to a contractor and they can come up with a very, very accurate idea of how much it's going to cost them to build it. Whereas, how do we cost buildings nowadays? Has anyone actually been involved in a project where you've had to like try and guess what the cost of a building is going to be? Maybe you've done some building work in your house growing up or something. No? Yeah? How did you work out how much it was going to cost?
Well, because when parents mostly build it themselves, we don't have a lot of labor costs that we have to And it was during COVID. We had to
Okay.
take into account a lot of the material costs.
Yeah.
Everything just went like skyrocketed.
So what you basically did manually was that you had to look at the design of the building, and then you had to say, okay, well, I need to order 72 sheets of plywood, and I need to order 13 meters of steel, and I need to order 3,000 bricks. I don't know, whatever. And then you go to a supplier and you say, hey, how much for 70 sheets of plywood? And they say, oh, I'll take one arm and one leg, please. And then also your kidneys. And then you go, thank you very much. And then you go and build your building. But if you can control that cost at an early stage, what you can do is you can adjust the design to suit the amount of money you have. And clients love this, because the reality of building a building is the traditional way of estimating cost is that you just take a guess. This is literally how people do it. People go to university to study quantity surveying, cost estimation, and really it's just a whole load of rules of thumb. I'm not going to do them down. It's very complicated rules of thumb. But basically what you say is, my building is 1,000 square meters. And it's going to cost me roughly, I don't know, for a cheap building, £1,500 a square meter. For an expensive, really high quality building, £2,500 a square meter. For like Daniel Liebeskind or Zaha Hadid, £5,000 per square meter. And then you just multiply it up. You just go, bigger is more costly. But if you can control that cost in a clever way, you can get bigger buildings to cost less. You get smaller buildings to cost more. You can control that whole process. Off-site is spelt wrong. I do apologize. Information to help people create things off-site, modules that connect on-site. So if you really want to control costs, the thing that everyone gets very excited about is off-site construction. If you've been to a building site, right? You've seen building sites, you've visited building sites. What's the thing that you notice about building sites first? What do you have to wear on your feet? Boots. Why do you have to wear boots? Everything is muddy. Everything is rainy. Everything is cold, even in the summer. Everyone is unhappy and grumpy. And everything is just bodge it. Just hit it with a hammer until it kind of fits. I'm generalizing, right? But that's kind of how building sites are. Yes, there is a lot of craft, there's a lot of complexity, but when you're in the rain on a Friday afternoon and the snow is coming down and the mud is everywhere, you're not going to do your best work. And you're not going to be able to be clinically precise about getting things exactly right. And maybe that's okay for most buildings, but if you're trying to design something which has very, very, very small tolerances, that you are so concerned that the particular gap between this wall and this suspended ceiling is exactly 50 millimeters and it won't do if it's anything less or more because you've got a certain thing to fit in there or whatever. The thing to do is to treat it like a factory, because in factories you can make very, very, very controlled manufacturing decisions, right? So wouldn't it be great if you could build a bit in a factory where it's dry and warm and controlled and you've got a robot arm or a CNC machine or something that you can be very, very precise about. And then when you're done, you ship it to site and you click it into place like Lego. That's the dream of modular construction. It's very difficult to do. And lots of people have started up companies with the dream of revolutionizing construction using modular. And the only way you could do modular construction is if you design it in a computer completely first, which is why you need building information modeling. So you don't just have information. Actually, this is not just about the t-shirt modeling information about what the product is. This is providing information to a factory to make a thing they've never made before, maybe 50 times, and then put it on a truck and deliver it to site on the right date, with the right size, with the right tolerances, with the right quality control. All of that information then becomes part of the building information model. Do you see where I'm going with this? This is going to be huge. This is going to then become, well, how big is a building information model? I I've seen models that are 2 or 3 gigabytes in size, and that's just mostly text and geometry. If you can plan construction processes in the right order and you reduce waste, you can save time, you can save cost, you can save carbon. I'll come back to carbon a bit in a minute. And then, of course, if you hand over your building to someone who's going to manage it, that facilities manager, and let's say, can you hear there's a little hum in the background of this room? I think that's probably mostly the projector. There's also the lights in the room. There's ventilation. I'm sure there'll be ventilation in this room somewhere. Yeah, you can see the vents on the walls. Now that vent will go somewhere to an air pump that's pumping fresh air into this room. The windows themselves have like mechanical things that mean they can open and close. Right, every single one of those needs to be maintained, because if it went wrong, we'd be having a terrible time. And wouldn't it be great if, as a facilities manager, you get the keys to your new building, and along with the keys to the new building, you have information on every single component in that building, along with its warranty, along with who you call when it breaks, and how long that warranty lasts. Well, that would be pretty cool, right? Because then if the pump gives you the fresh air after 3 months, you don't have to go, who was that guy who came and fitted it? And we need to ring him back. And will he fix it? Will he cover the charge, or will we have to pay him? You've got all the information there at your fingertips. If you maintain something, it also lasts for a lot longer. You have to buy a new one and then dig up precious metals from the earth in order to make a new air source heat pump or whatever it might be. And if you can do that well, you can reduce your operational carbon as well as the carbon associated with the actual building itself. One of the things that Grenfell has done is force architects to change the way that you design buildings. And I'm going to use this phrase, but I'm imagining that you may not have heard it yet. It's called the golden thread. Have you heard this phrase before? No, some of you have, some of you haven't. Okay, so the golden thread of information is picking up on exactly what I said about Grenfell, which is people didn't have the right information at the right time to make an informed decision about whether something was safe or not. And also, what happens when you start a project, this is kind of the real world of architecture, is you change your minds about things. Clients change their minds. Clients find out they don't have as much money as they thought they were going to have. Contractors go bust. You've got to find a new contractor. The subcontractor doesn't understand what they're supposed to do. They deliver the wrong things to site. It's just chaos from start to finish. And during that time, one of the things that as architects we have to do is we have to collaborate with all these people, and often we'll make design changes. So like Alvar Aalto, did he sit down, draw the building, and then sit back, pass it over to a builder, and it came out exactly how he thought? Of course not. If you're the kind of guy who obsesses over door handles, you are visiting that site most days, probably every day. And you are there to make sure that it gets built the way that you want it to. And when the builder comes to you with a problem and says, we ordered the steel and it's 5 centimeters too short, what are you going to do? You've got 2 choices. You send it back and reorder the steel. How long is that going to take? 3 weeks? 6 weeks? New bit of steel? How much is it going to cost the client? Another £1,000. No one's going to be happy with you if you do that, because you've got to wait now, because the steel was going in today and it's 5 centimeters too short. I'm feeding back for some reason. So that's one choice that you could make. You can piss everyone off. Or you could say, right, okay, if we move this wall a little bit this way, and if we, let's go back to the drawing, if we push this just a tad inwards this way, and if we change maybe the structural way in which that beam is supported, maybe we can make that work. Let me give the structural engineer a call. Hey, if I do this and this and this, is that going to work? And the structural engineer goes, yeah, that's fine. And so you've changed the design. This was what he drew in his mind, and now the actual things come out different. Maybe it's only 5 centimeters different, but that could mean the difference between life and death sometimes. So what the question is how do you track all of those changes that you have to make as you respond to the constraints and the desires and the needs of everyone else who's collaborating to design this building. And the golden thread is basically saying you need to have a thread of information on every design change that you choose to make, so that anyone looking back can say, I understand why we did this. It's because of that. And here's the information I need to respond to it. Because if you didn't then communicate that, you just say, it'll be fine. And you put the beam in, it's 5 centimeters too short, and it falls off the stone, the masonry that it's supposed to be sitting on. And the whole thing falls over and kills a construction worker, or falls on the family when they move in. Well, whose fault is that? Sadly, a lot of the time, the architect gets blamed. So the golden thread is about protecting yourself. This is why BIM becomes really important and very stressful. Are you feeling a little bit stressed now? You feel like maybe I don't want to be an architect after all. I might kill people. Well, the reason for all of this stuff is it's a little bit like the airline industry. In the airline industry, everyone's worried that you're going to die in a plane crash. Everyone's worried about safety. But then the response of the industry is to take safety really seriously and put processes and systems in place that mean that those accidents are much rarer. Very, very rare indeed. The airline industry is incredibly safe because of those systems and processes. So what building information modeling does, it gives you a scaffold for making sure that that stuff is tracked. You don't have to worry about it. It's just done. This is the kind of thing that happens on building sites nowadays. I'm pretty sure there will have been some kind of robotics, maybe not a Boston Dynamics, but I know that we were using printer robots. They're little, I'm going to find a little picture of one. I think it is printer robot construction. HP Site Print. HP make printers, right? They also make this little dude. Look at him. Just rolling around. And look what's happening. He just rolls around on the site and he prints the floor plate onto the floor. Let me try. Yeah, here we go. Can you see all of this stuff? I think they were using this on the Brooks building. And right at the beginning, when I said there's this disconnect, right, between what the architect draws and then someone sort of puts a stick in the ground and then just paces out and then puts another stick in the ground. There's a complete disconnect there. This guy here means that you design the building, you say the wall is going to go here. Well, then that digital file gets sent to a little robot. The robot knows exactly where it is in the building because it's got GPS, it's got a little point cloud, it's got LiDAR, all these things. And the robot draws a line on the floor that's one-to-one exactly where the wall is going to go. And then you can be, any kind of person on the site. You don't even have a question anymore. Where's the wall going? Well, there's a big line on the floor. Put the wall there. This is good for architects. This guy here, this example, they use this a lot in the United States. There's a point cloud scanner mounted on top of the robot. And what happens is every morning, I think they do this overnight or in the morning, before everyone comes onto the site, the robot dog walks around the building site and scans the whole thing, makes a point cloud, a 3D point cloud. Do you remember right at the beginning, we did 3D point clouds? I made one on my phone. This is just like a really expensive version of that. But it scans that and then produces a digital model of what you're doing. And then you can compare that to the model that you've made and say, hey, listen, this pipe that the engineers installed is 2 feet to the left and it should be over here. There's a problem. And you catch it well before it becomes a real issue. So what you're doing is you're bringing together the digital world in which you work and the construction world in which you actually are producing a building. Here's an example. So this is the digital model of a building, and this is the point cloud that the robot goes round to collect, and then you can sort of basically overlay the two and you can see where they differ. Let's talk about carbon. This is the UK's carbon emissions. This whole bar along the top. 58% of it comes from people who aren't associated with architecture. 42% of it comes from you guys. Are you feeling responsible? Are you feeling a bit worried about the process of becoming an architect? Well, I'm going to kill people and I'm going to destroy the planet. Well, hey, me. 42% of all of our carbon emissions come directly either from the built environment or from transporting things around that we need in the built environment. So we've got a massive amount of responsibility to try and reduce that as much as possible. There are two ways we can reduce our carbon footprint in architecture. One is to reduce the embodied carbon, which means this building almost certainly is held up using steel. Steel, very, very carbon intensive to produce. If instead I was to use something like timber, which has a much lower carbon footprint, to do the same thing, I've reduced the embodied carbon in the body of the building. There's less carbon emissions associated with the body of the building. It's also, the embodied carbon is also the carbon that gets produced when you are building the building. So if you use a technique that uses less energy whilst you are manufacturing, you've saved embodied carbon there as well. Off-site manufacturing promises to save embodied carbon because rather than using a really inefficient generator on a site, you can use a very, very clean power source in a factory. You see where I'm going. 33% of the carbon emissions come from the embodied carbon of the building. But 67% is the carbon emitted during the life cycle of the building. So I'd imagine it like this. It's double the carbon cost to keep this building hot, lit, working, ventilated, as it was to build it in the first place. Because the whole life cycle of the building, you think, oh, well, the gas bill's only, I don't know, how much is the gas bill for this building? It's probably decent. Oh, it's only a few £1,000s a month. But that adds up over a 50-year lifespan to more than what the carbon impact was of actually building the thing. And that's the reason why we say that the most efficient building is the one that already exists, because we're reducing our embodied carbon. But we can't just leave it as it is, because we're going to keep using operational carbon to keep it lit, keep it hot, keep it from freezing, keep it fed with utilities, all of these things. So what we want to do, especially if we're working with an existing building, is try and make it so that operational carbon is as good as possible. And again, in order to do that, we need information. I'm going to move on now, and we'll actually have a look at some things. But I want to give an opportunity for some questions here, because I've kind of rattled through the state of the entirety of the architecture sector. And I'm aware that I probably have gone into, so I've touched on some things that you may have questions about, or you may be thinking, I'm not sure about that, let's ask. So let's take 5 minutes and see if there are any questions and make sure that we're kind of happy with where we are before we carry on. About anything.
How does modular construction should increase transportation costs, right?
Yeah.
Does that not emit more carbon?
Generally speaking, transportation costs in construction are not as big of a factor as everyone thinks they are. So usually, the promise of modular construction anyway, usually the carbon savings that you can get from being really efficient about where you make things and how you make things, and really efficient about repeating patterns and molds and manufacturing techniques that basically kind of Like it gets really efficient if you make 50 of the same thing, right? Whereas on a construction site, you're making one thing with a hammer, and then you sort of stop, take a tea break, and you make another thing with a hammer, and then go do that 50 times. If you can be really efficient about how a factory produces that, it well outweighs any transportation costs. The difficulties with modular construction are often the fact that it's not that the cost of the transportation is a problem, it's often just the practicalities of it. So this is a bad example for modular constructions, right? Oh. I want to find the image of this in the... Where are we? I want the image of this thing. This is the Alvar Aalto. Here we go. This is Alvar Aalto's Villa Maria. We looked at the floor plan, but now let's zoom out. How are you going to get an 18-wheeler like truck with a modular thing on the back of it that needs like a police escort down the motorway? How are you going to get one of those to here? Well, that's mostly the thing that trips people up, is access and planning and also timescales. So you need to have the design finished in order to send the design to the factory so the factory can build the thing, and they might have like 10 weeks to do it. And so you need to know before you get there that the building site's going to be ready. But if you get set back, then are you just going to let the truck go with all your stuff on? Are you going to pay for it to be delivered again? And all of that, that's the kind of logistics and admin of it. That's the thing that really kills modular construction, or can often do. Yeah, you got a question?
This is just more of a fun sort of question. Do you realistically see in the future people dropping in like components for sites?
Yeah, I think it's a really interesting question, and the reason I think it's an interesting question is not because of the airdropping, but although like Amazon have been experimenting with drone delivery, right? Like I'm not sure how far they've really got with it. I think it's more of a gimmick than anything else. Maybe these kinds of sites, people already do use helicopters. Like, but only if you're like a super rich person who wants to build a house on the side of a mountain, and you want to be like, that's what you want, and that's the only way of getting it. You just go, okay, I don't care about the cost, I'm just going to do it. Helicopters are used all the time for inaccessible places, and they usually in infrastructure more. But the point that you're making is actually an interesting one, because when you stop and think modular construction, well, when we talk about a module, what do you have in your mind when you think about modular construction? Like, what sort of size and scale are you thinking about when you think about, let's build a bit of this building and then ship it to site? What's the kind of scale?
Either in like a set, sort of like a panel.
Yeah.
But then I've seen some projects on like grand design where they just do a whole wall.
Yeah.
A whole face of the building.
Yeah.
It comes together like a gingerbread house.
Yeah. So like actually quite massive things, right? These are huge. And generally speaking, the economics of it are such that you have to do these big things in the factory to get the positive outcomes, because otherwise you just do it on site. What's interesting is to think about, well, could it be modular but smaller things that people can carry? And that's where you kind of stop and realize that we're already building modular ways. So we build using sheets of plywood that are standard sizes, sheets of plasterboard that are standard sizes. Why are they the size that they are? They're 1,220 millimeters by 2440 millimeters.
Fit inside shipping containers.
No, well, maybe they do, but what's the main reason for them being the size they are?
I was going to say that it's just easier to replace.
Yeah, well, they're all standard, so they're all the same. So you could just go to the shop and buy another one. Yeah.
Is it
Partly, yeah, they can fit through doorways, but who's carrying them through a doorway?
It's sprinter vans, isn't it? Like builder's vans?
Yeah, but I mean, if you changed, if they had a different standard size, they just make the sprinter vans a different size.
Well, how big can something be for like one person to carry?
Boom, you got it. How big can something be for one person to carry? Why is a brick the size that a brick is? Because a person can hold it in one hand. Because the person who's going to do the building is one person. So if you made a brick that was too big to carry in one hand, you could only carry one at a time, and it would suddenly be like not quite as efficient anymore. So a sheet of plasterboard or a sheet of plywood, I think if you pick one up, they're heavy, but you can just about. I mean, if you work on a construction site, you probably just pick up 3 at a time because you're hench. But when I pick up a piece of plywood, I'm like, I can just about carry that through a doorway, put it where it needs to go, boom. So it's like bigger than a person, but not much bigger than a person. So like we were just saying, that whole facade of a building, that's not a very human-friendly scale to be producing a module of. Because then suddenly you need trucks, you need vans, you need cranes, you need hydraulics, you need to really plan things out. If you had modules, and various people are working on this, modules that are a bit more human sized, and that means the whole house sort of clicks together like Lego. Modern roof tiles are like that. You don't need like cement or concrete or anything like that, or anything to. They just literally just click together on a roof. And so what you're trying to go for is like something in between. I think this is going to be the interesting thing. So your drone question, it raises the question of like, well, how heavy can something be whilst it's still delivered by a drone? Well, also, how heavy can something be while also still being lifted by a person? How big can something be while also still being lifted by a person? And actually, the construction industry has done a lot of work to kind of standardize a lot of those things as much as possible. But we're still in a bit of a kind of 100 years ago mindset about the fact that someone's going to put this brick together with cement that uses a whole load of carbon. Maybe it's about bricks that slot together or something. I don't know. Yeah.
So what about software? Like, are you going to show us softwares that are used for BIM, or?
I'm indeed. So I'm going to spend the next hour talking you through a real project. Any other questions, or should we take a break and then we'll dive into some real stuff? Cool. 5 minutes. See you back at 10.